Okay, in this podcast we're going to talk about significant digits, sometimes called significant figures, and often called sig figs. That's usually how I refer to them. And you can think about sig figs as where to round. That's usually the question you're trying to answer, is where to round. Or answering the question, how many digits to report. But simply, significant digits are measured plus uncertain numbers, just like we were talking about in the last podcast, right? We always measure to the smallest line, smallest grid line, let's say on a graduated cylinder, and then we estimate one more digit, okay? And these tell scientists how precise the measurements they are looking at are. Okay, so what are the rules? So first of all non-zero are significant. So what that means is if I have a number 1.32375, all of these are significant. So this number has 1, 2, 3, 4, 5 sig figs. Okay? Now, also, if I have 1.2075, any zero that is sandwiched between non-zero numbers are significant. So this also has 5 sig figs. The question you have to answer when you're talking about sig figs are whether or not zeros are significant. And it's only zeros that we're concerned about that may or may not be significant. So the rules on zeros, so this is the zeros rule, is placeholders are not significant. It's not part of the measurement. We just need it there to indicate magnitude. So for instance, if I have 0.0011 grams of something, these 3 zeros are there to hold place, because I can't write this number as 0.11 grams, right? It's not. It's there to indicate magnitude or to hold place. So this number would only have 2 sig figs. Okay? So decimals, if a number has a decimal, it's all leading zeros are not significant. Okay? And all trailing zeros are not. Those are there just for place, not significant. Okay, so if someone said, how many students graduated from East High School in the year 2010, and we said 2,000, we cannot assume that these are significant. This might be just a rounded number. So this number would only have 1 sig fig. Okay? So placeholders are not significant. So 0.0011, leading zeros, when there's a decimal, are not significant. Trailing zeros, when there's no decimal, are not significant. Okay. These 3 are there to indicate place. So this only has one sig fig. Okay. 2000, this ends, this is a non-decimal number, so trailing zeros are not significant. So there's only one sig fig. Now here, these three are not significant because they're there for place. But this one is significant because there's only one reason to report that, and that is because I know it, right? Otherwise, I would report this as 0.001. The difference between 0.001 and 0.0010 has to be the precision of the measuring equipment. I know this one with greater precision, okay? So trailing zeros when there's a decimal are always going to be significant. Okay, so what about exact numbers? So if I say there are 10 boys in this classroom, that is a counting number. So exact numbers are counting numbers. They are not measurements. Okay, they are counting numbers, they are not measurements, and they have what's considered to be an infinite number of sig figs. So they do not constrain the calculation that we do with them, okay? So 10 has an infinite number of sig figs, okay? I could say there are exactly, I counted, and there are exactly 100 styrofoam balls in that box. And if I know there's exactly 100, that's a counting number, okay? So we also don't, when we have a definition, when we say, for instance, there are 2.54 centimeters equals 1 inch, we don't, these are definitions. They are not measurements, and therefore they have an infinite number of sig figs. They do not count in terms of limiting us when we calculate with them. Okay. Let's determine the number of sig figs in these. Okay, so these are the only two. The leading ones are not, so this has 2. This has 4. This is sandwiched, so all 5. If I look at these, leading zeros or not, I have 4 sig figs. Because there's a decimal here, these are significant, so I have 5. And if I look here, all of these are not significant, but this one is, otherwise, why write it? So this is 4 sig figs. Okay, so what is scientific notation? It is a shorthand method for writing out numbers, and it uses exponents or powers of 10. Okay, and where is it used? Well, it's used when we have really large numbers. For instance, if you were to ask me how many atoms are in the head of a common pin, I would tell you it is a million billion, and or I could say 1 times 10 to the 12th. A lot easier to say this. Or when I have really small numbers. So if we're talking about the mass of an aluminum atom, it is going to be 4.5 times 10 to the minus 23 grams. If I wrote that out, it'd be 1, 2, 3. I'm getting lazy. But there'd be 23 zeros and then 4.5. You know, you're not going to be writing those numbers. So we use really small numbers and really large numbers all the time in chem. When we're talking about how many atoms, really large numbers. When we're talking about how much they weigh, really small numbers. Okay, so let's convert these between scientific and standard form. So, the rule is scientific notation always has all numbers are significant digits or significant figures. Okay, so what that means is these are the only three significant digits, so I want to include all of those in the coefficient. And the rule is there's always a one non-zero digit to the left of the decimal, so it's 3.69 times 10 to the something. So what I do is I count how many decimal places I have to move, how many places I have to move the decimal point. And right here, the decimal point is right here on this number. So I go 1, 2, 3, 4, 5. Okay. Here, I have 2.4 times 10 to the 8th. So I'm going to move the decimal point from here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. So that would be longhand, right? Standard notation. These are significant digits, so I'm going to include 7, only one digit to the left of the decimal, 7.12, times 10. Because I'm making a decimal, a really small number, I'm going to have a negative exponent, so moving it towards the right. 1, 2, 3, 4, 5, times 10 to the minus 6. 5 times 10 to the minus 4. Okay, so this must be significant because it's there, so I need it there. And I have 1, 2, 3, 4. So that would be that number written in standard form. Okay. Okay, so how to use a calculator with scientific notation. The key thing is you want to use either EE. So if I were writing this number, punching this number on my calculator, let's say I have 1.4 times 10 to the minus 3. What I do, punching in my calculator, is 1.4. Most calculators have EE, and then I say negative 3. Or some calculators don't have the EE, they have the EXP, and instead of EE, I put EXP. What you don't ever want to do is say times 10, because what that does is if I say times 10 and I have minus 3, it takes the minus 3 exponent and multiplies that times 10, which makes it times minus 2. Okay, so do not use the times 10. Also, don't recommend you use the caret. You got to use the EE or the EXP key. Okay. So why is it important to keep track of the number of significant digits? Well, it reflects the precision, and so it's of the measuring devices. So it communicates that to the reader, someone who's looking at your measurements. So it's important that you not report a number that indicates you have more precision than you actually do. Okay, so this is communication. It's a communication. It's implied in the numbers. Scientists know how to look at those numbers and determine how precise it is. Okay, so one of the rules is that we can, when we look at calculations using measurements, we cannot make a measurement more precise by performing a calculation. And we can also say that a calculated value cannot be more precise than the measurements used in the calculation. So if I am using a bathroom scale to measure the amount of table salt, I can't multiply that number and make it any more accurate than it is. It's very imprecise because it used the bathroom scale. Okay, so we're going to take a look at the rules for significant figures and calculations. First, we'll talk about addition and subtraction. It's different for addition and subtraction than it is for multiplication and division. Okay, so the rule for addition and subtraction is we want to round to the number of decimal places. I'm just going to abbreviate it DP, decimal places as the factor with the least. Okay, so here's an example. I have 865.9 minus 28121 milliliters. I'm going to use my calculator and punch it, and my calculator says 863.09, but your calculator doesn't know how to round to the right number of sig figs. What I have to look at is this has 1 decimal place, this has 4 decimal places, so I want to report to 1 decimal place. So I want to round that number, and because this is a 9, my answer is going to be 863.1 milliliter. Okay? So try this one. Okay, my calculator says 106.78, and 1 sig fig, I'm sorry, 1 decimal place, 2 decimal places. I want to round this number, so it's going to be 106.8 milliliters. Okay, the rule for multiplication and division, which we do much more commonly in science and chemistry, is to round to the lowest number of sig figs of any of the factors. Okay, so if I have measured a rectangle and I know that one side has 6.09 centimeters, one side is 9.2 centimeters, and the other side is 3.3418 centimeters, I want to have an answer that has a number of sig figs which represents the least of these three. So this has 3, this has 2, this has 4. So my answer can have no more than 2. This measurement constrains how many sig figs I can have in my answer. Okay? All right. The other thing we want to be careful about is we want to round up when we have 5. So if I have 10.5 and I want to report that to 2 sig figs, it's going to be 11. If I have 10.4 and I want 2 sig figs, that becomes 10. Okay, so I put a different set of numbers here because I want to make a point than you have in your packet. We don't round until after the last calculation. Otherwise, we are propagating error. Let me tell you what I mean by that. Here's an example. So if I take this number and I punch in the numerator, and this has 3 sig figs, this has 4 sig figs, and I round that to 1.77. My calculator says 1.77 something. But if I round it to the right number of sig figs, and I do the same thing for the denominator ends up being 0.14. And then I divide those two, and I want to report to 2 sig figs. My answer ends up being, let me see, 12.642 is what my calculator says. I want to report 2 sig figs because that's what this is. My answer becomes 13. Okay. Now, if I were to take these numbers and leave it in my calculator, or pick this one up and then divide by these in parentheses, my calculator says the answer is 12.407, which rounds to 12. 12 is the correct answer. 13 is the wrong answer. And you might look at that and say, well, 12 is close to 13, but you know what? If I reported the answer to be 13 instead of 12, that represents an 8.3% error. Now we're going to talk about error how to calculate this in class, but this is a large error. We consider anything greater than 5% error to be significant. So we have created an error based on our calculations when none existed. Okay, so let me stop there.